Jupiter didn't need to collide with 3i Atlas, it only needed proximity. And on the morning of November 24th, that proximity became measurable, not as a visible flash, not as a gravitational anomaly, but as a pattern, subtle, structured, and unmistakably deliberate in its geometry. What entered Jupiter's outer magnetic influence wasn't just a comet brushing past. It was an object behaving like it understood the spatial boundaries it was entering. At 4:44 a.m. Universal Time, Jupiter's outer magnetotail, more than 60 million kilometers from its center, registered a deviation in local plasma velocity. This region, typically chaotic and influenced by the Sun's fluctuating solar wind, suddenly aligned. Charged particles began forming lanes, not random, not diffuse, but directionally coherent streams that all pointed downstream from a singular reference point. That reference point was 3i Atlas. Unlike the flyby of Mars or the deep atmospheric brushing against Venus, the approach to Jupiter was characterized by a complete shift in how the object behaved. Where previous encounters left chemical residues and short-term perturbations, this interaction began with something else: synchronization. Jupiter's influence extends further than any other planetary body in the solar system. Its magnetosphere is vast, dwarfing even the Sun's in sheer complexity. For 3i Atlas to enter that zone and not be absorbed, deflected, or scattered into inert drift meant something was being respected, or exploited. What instruments picked up in those early hours was not a typical wake effect. It was formation. Thin trails of ions, neutral particles, and energized dust began tracing arcs, some of them spiraling inward, others outward, but all centered around a single moving node. This node was not Jupiter. It was the moving shadow of 3i Atlas passing through a magnetized sea. The directionality of the trails was the first clue. Instead of dispersing radially, like exhaust from a natural object, the particles laid themselves out like scaffolding. Spacecraft sensors detected rhythmic variations in density every 22.4 seconds. That number didn't correspond to any known Jovian resonance. Not moon orbit, not rotation speed, not solar harmonics. It was new, and it came with mass. Within 90 minutes of 3i Atlas entering this influence zone, nickel particles were detected by the Italian-built dust impact sensor aboard ESA's JUICE spacecraft. Once again, refined. Once again, separated from iron. But unlike at Mars, where dust settled inertly, these particles began spiraling into the ambient fields, not tumbling randomly, but falling into step. The pattern wasn't gravitational, it was electromagnetic. This marks the first time in modern observation that an object passed through Jupiter's outer domain and left behind a measurable change to its structured plasma architecture without being captured or disrupted. The object maintained velocity, it didn't fragment, and yet the particles it emitted began behaving like relay nodes, anchoring into the Jovian system with precision. To put this into planetary scale, if Jupiter were the size of a house, this interaction would have taken place from 5 miles away, and yet still reorganized the lights on the front porch. What's even more significant is what didn't happen. Jupiter did not deflect 3i Atlas. It didn't tear it apart. Instead, the two bodies passed each other like ships on a mirrored sea, each reflecting subtle changes in the other's wake but never colliding. What changed, however, was the medium between them. That's what researchers are still parsing, because this wasn't a flyby, it was a handshake, and it began with a pattern. Jupiter's magnetosphere is the largest known structure in the solar system, extending millions of kilometers into space, far beyond the orbits of many of its moons. It is powerful, dynamic, and resilient to even the most aggressive burst from the Sun. But on the morning of November 24th, it did something it rarely does. It twitched. To an untrained eye, a twitch in a magnetic field might seem inconsequential. But to planetary scientists and plasma physicists, a twitch is a coded event. It means the field did not simply bend under pressure or compress from solar wind. It moved, sharply, suddenly, and with directionality that cannot be attributed to solar interference alone. The initial anomaly was logged by Juno's MAG instrument, which measures vector changes in Jupiter's magnetic environment. At precisely 4:51 a.m. UTC, it picked up a deviation of 0.3 nanoteslas Not a large number in absolute terms, but statistically outside of modelled fluctuations for that region of the outer magnetosphere. The change wasn't chaotic, it was smooth, like a ripple from a dropped stone, propagating outward, then recentering. The key word in the telemetry was coherence. Normally, Jupiter's magnetic field absorbs energy from the solar wind and redistributes it in controlled auroral emissions near its poles. These emissions are structured and predictable. But after 3I Atlas entered Jupiter's outer magnetotail, something subtle shifted, not in brightness, not in frequency, but in rhythm. The plasma sheet that extends behind Jupiter, essentially a river of charged particles shaped by the planet's magnetic dominance, registered a pressure increase. That by itself was not unusual. But the spatial profile of the increase was unlike anything the Juno team had seen before. Instead of spreading symmetrically from the center line, the pressure formed a sharp angle, like a hinge. Imagine a curtain being pulled slightly to the side by an unseen hand. That's what the telemetry showed. A diagonal crease in the field, and at the center of that crease, the calculated position of 3I Atlas's plasma wake, now interacting with Jupiter's outermost field lines. This was not just passive turbulence, it was directional, interaction. Magnetic field models that account for solar wind, moon influences, and internal dynamo activity could not explain the angular torque. And when teams began ruling out solar input, no coronal mass ejection, no sudden flare, no interplanetary shockwave, the conclusion became harder to avoid. The cause was local. To appreciate how significant this is, consider that Jupiter's magnetosphere is powerful enough to strip atmosphere from its moons, trap deadly radiation for years, and distort the very shape of the solar wind around it. For it to twitch requires an input that does more than nudge. It needs to push with precision. And that's exactly what seemed to happen. The notion that an object the size of 3I Atlas, a relatively small interstellar visitor, could induce even a momentary asymmetry in Jupiter's magnetosphere challenges fundamental assumptions about both the comet and the field it encountered. But the data is clear. The field bent, not from inside, not from solar force, but from something moving past it. Post-analysis revealed secondary harmonics in the mag data, faint, repeating, and spaced every 3.6 seconds. This spacing is not random. It mirrors emission patterns seen at Mars when 3I Atlas passed, pulsed harmonics, like a signal, or a consequence. The term resonance induction has now entered internal discussions at multiple mission labs, not as a definitive explanation, but as a placeholder. Because what was observed that morning can't be dismissed as noise. The magnetosphere twitched, not like a shield under attack, but like a sensor responding to contact. Something passed through Jupiter's magnetic skin, and Jupiter noticed. Jupiter's plasma environment is not passive. It's sculpted by motion. Jupiter's rapid 10-hour rotation, its strong magnetic field, and the relentless flow of charged particles from its volcanic moon, Io. The result is a swirling, ever-replenishing torus of plasma circling the planet in tightly wound spirals, perfectly synchronized with Jupiter's rotation. That is, until the loops started curling in the wrong direction. At 5:03 a.m. UTC on November 24th, the Jovian Energetic Particle Detector instrument, JEDI, aboard the Juno spacecraft detected a sudden asymmetry in electron flux along the magnetic equator. Normally, the plasma loops within the Io torus follow clear centrifugal arcs, spiraling outward as they rotate around the planet. But now, a portion of these loops had begun bending inward, against the flow, against the geometry, and most importantly, against the physics we thought governed that system. Initial readings were dismissed as sensor artifacts. After all, plasma doesn't just reverse direction in one of the most stable electromagnetic structures in the solar system. But the anomaly persisted, and within 17 minutes, other instruments confirmed the change. The WAVES instrument, designed to detect plasma wave emissions, picked up harmonics characteristic of compression, not expansion. The loops weren't spiraling freely, they were contracting. Picture a set of racetrack lanes suddenly bowing inward, as if a magnetic lens were being applied from the outside. But there was no lens, no object within the system large enough, charged enough, or close enough to account for this. Except one 3I Atlas. But Atlas was not in the torus. It was skimming the outer magnetosphere, far beyond the region of influence where Io's plasma normally circulates, and that's what made this so strange. The source of the disturbance was nowhere near the loops that were responding, so how was it happening? One hypothesis began to emerge: field line resonance transfer. Essentially, if a structure like 3I Atlas carries a tail of ionized material long enough and moves through a planetary magnetosphere at the right angle, it can act like a string dragged across a guitar. Even without touching the strings directly, the motion induces harmonics, energy oscillations that propagate along magnetic lines. And in the complex magnetic topology of Jupiter, where field lines interconnect between equator, poles and moons, that oscillation could travel. What Juno was seeing wasn't random turbulence, it was a response, and it was targeted. The inward-curled loops weren't spread across the torus, they were localized, concentrated within 30 degrees of magnetic longitude, centered precisely on the calculated intersection angle of 3I Atlas's tail with Jupiter's midfield zone. This meant the plasma wasn't simply disturbed, it was being pulled, organized, toward a geometry that reflected external influence. Secondary evidence came from the JADE instrument, which recorded an unusual concentration of H+ and O+ ions, accelerating toward the magnetic equator. Normally, these ions spiral outward. Their inward migration was unprecedented, and could only occur if the electric field orientation itself had shifted, if only briefly. And here's where it gets more speculative. Some researchers noticed that the curling loops weren't static. They appeared to be tightening over time, drawing in closer to Jupiter's mid-latitude magnetic planes in a self-reinforcing pattern. In effect, the system was building a feedback loop, not just responding, but learning. Now consider the implications. Jupiter's plasma torus is massive, spanning nearly half the planet's circumference. Any structural change within it affects radiation balance, auroral generation, and magnetic coupling with moons like Io and Europa. If 3I Atlas initiated a change in the system, it didn't just rattle the outer magnetosphere. It reached into the planet's core magnetic engine and twisted it. The loops are still curling, and Jupiter isn't pushing back, it's adapting. There's a reason planetary chemists are so alarmed by the repeated appearance of nickel, refined nickel, in the wake of 3I Atlas. It's not because nickel is rare, it's because refined nickel isn't supposed to appear in space at all. On November 24, 2025, Jupiter's outer magnetosphere confirmed what Mars and Venus had already suggested. The object known as 3I Atlas was distributing high-purity, industrial-grade nickel into planetary systems it passed. But this time, the fingerprint didn't land on a rocky surface, or dissolve in corrosive clouds. This time, it entered an electromagnetic crucible, Jupiter's magnetosphere, and something happened that can't be explained through natural cometry processes. It began with the detection of an anomalous spectral line by the Particle Environment Package, PEP, aboard ESA's JUICE spacecraft. Positioned near the outer edge of Jupiter's magnetodisk, JUICE logged ionization frequencies consistent with Ni+, or singly ionized nickel. Not unusual in itself, except for the intensity. The emissions were strong enough to suggest localized concentrations 10 times higher than background, and once again, no iron. This violates a fundamental rule of cosmic chemistry. Iron and nickel form together in stars, condense together in protoplanetary disks, and are almost always found in locked ratios. The universal average? About 18.1, 18 atoms of iron for every one of nickel. And yet here, again, the ratio was inverted. No iron lines were detectable. Just nickel, refined, concentrated, free-floating and charged. This was not a one-off detection. For nearly 40 minutes after 3I Atlas passed closest to Jupiter, particle detectors across multiple spacecraft recorded repeat samples of these nickel ions, moving in a narrow band like a chemical ribbon, cutting across the planet's magnetic equator. Their trajectory didn't match that of ambient particles in the Jovian plasma environment. Instead, they followed a sharply defined path, suggesting they were not dispersed dust from cometary shedding, but part of a collimated emission, a targeted release. This aligns with previous encounters. On Mars, a refined nickel appeared embedded in the regolith, unnaturally pure, with crystalline structuring that resembled industrial metallurgy. On Venus, nickel was captured by the upper sulfuric acid clouds, forming compounds only stable in synthetic lab environments. And now, here at Jupiter, the pattern repeated, but with an added twist: motion. Juno's JADE instrument picked up the nickel trail moving perpendicular to the typical corrotation flow. That is, it wasn't being dragged along by Jupiter's magnetic field like most ions. It was resisting that pull, cutting across it. This suggests either initial kinetic velocity or active electromagnetic shielding. Either way, natural cometary ejection mechanisms cannot explain the behaviour, so the question arises again: how is this nickel being refined, and why is it being released in structured paths? The leading hypothesis, still whispered behind closed doors, is that 3I Atlas underwent a natural process similar to the Mond method, an industrial technique used on Earth to separate nickel from iron using carbon monoxide. Under this theory, volatile conditions inside the comet allowed for the selective vaporization of nickel carbonyl, which then decomposed into pure nickel under solar radiation. But even if this occurred naturally, the persistence of that signature across multiple planets, and now within Jupiter's magnetosphere, implies more than just coincidence. It implies repeatability. Nickel is more than just a metal. In catalytic chemistry, it's a tool, a way to accelerate reactions, lower activation energy thresholds, and build complexity from simplicity. On Earth, it's used in everything from hydrogenation to battery development. In space, its appearance, isolated and reactive, is both rare and potentially transformative. So what does it mean when a non-native object deposits refined nickel into the largest electromagnetic system in our solar system? It means the system is being seeded. Whether by accident or intent, Jupiter has now absorbed a new ingredient, a fingerprint that carries with it the memory of process. And that process is not native to any comet we've ever studied. The fingerprint is there, and it's spreading. The moment 3I Atlas pierced the edge of Jupiter's magnetosphere, something subtle but measurable began to unfold in the space around it. It wasn't dramatic, it wasn't visible, but it was fundamental. Atoms began trading electrons. This process, called charge exchange, isn't rare in space. In fact, it's one of the primary mechanisms by which planetary magnetospheres interact with the solar wind. But what happened on the morning of November 24th wasn't typical solar plasma behaviour. It was localized, synchronized, and directional. The patterns indicated that 3I Atlas wasn't just passing through space, it was triggering responses in it. Let's break this down. Charge exchange occurs when a high-energy ion steals an electron from a neutral atom, creating a new ion and releasing radiation in the process. This usually happens in diffuse regions where energetic particles interact with atmospheric gases, like Earth's auroras or Jupiter's glowing limb. But what happened today occurred far from Jupiter's main atmospheric shell, in the magnetotail, where densities are low and interaction times are brief. At exactly 5:12 am UTC, JUICE's neutral and ion mass spectrometer, NIM, detected an increase in hydrogen atoms losing their electrons, not gradually, instantly. A wave of stripped hydrogen passed through the region near the outer magnetic sheet, followed closely by spikes in oxygen and carbon ions behaving the same way. This is key. The signature wasn't isotropic. The ions weren't spreading randomly. They were curling inward, converging into thin arcs that traced back toward 3I Atlas's projected tailpath. Think of it like contrails behind an aircraft, but made of chemically altered atoms. And then came the conics, formation. The ESA plasma wave instrument aboard JUICE detected emissions that traced the curvature of a cone. Its base aimed at Jupiter's magnetic equator, its tip aligned with the tail of the comet. These weren't weak radio signals. They were strong enough to saturate part of the detection bandwidth for over 40 seconds, creating a perfect V-shape in the instrument's frequency-time plots. So what causes a charge exchange cone? On Earth, this type of signal only forms in controlled laboratory conditions when directed ion beams interact with neutral gas clouds under magnetic confinement. In Jupiter's environment, the only plausible explanation is that a moving ion source, 3I Atlas, was trailing a cloud of energetic particles that met a denser band of neutrals inside the Jovian sheath. But there's a problem with that theory. The densities required to produce the observed magnitude of charge exchange exceed what a typical comet should be able to generate. Even at close range, 3I Atlas shouldn't have had enough mass or speed to inject this much ionized material into Jupiter's plasma environment, unless what it carried was chemically primed to trigger the reaction. And that's exactly what the nickel data seems to suggest. Nickel, particularly when refined, acts as a catalyst in charge transfer reactions. On Earth, it facilitates hydrogenation and electron flow in various organic and industrial processes. In space, if nickel nanoparticles or charged surfaces are present, they can enhance ionization cross-sections, effectively amplifying the probability of charge exchange, and refined nickel was there. It had already been logged. So the process may have gone like this. 3I Atlas's tail introduced a high concentration of ionized and neutral particles, some of them embedded with catalytically active metals. These particles entered Jupiter's outer magnetosphere, met with trapped neutral atoms in the magnetic sheath, and initiated chain reactions that exchanged charge faster than expected. This wasn't passive diffusion. It was induced activity, and here's where it turns. The structure of the exchange region didn't collapse after the initial spike. It stabilized, meaning that the ion funnel continued cycling particles even after the comet's tail moved on. What was left behind wasn't just a zone of exchanged atoms. It was a reactive corridor, possibly self-sustaining through the influence of Jupiter's own magnetic field. In short, 3I Atlas didn't just pass through Jupiter's environment. It triggered a transformation in it. Europa, one of Jupiter's most intriguing moons, is no stranger to radiation. Orbiting deep within Jupiter's magnetosphere, it constantly absorbs charged particles funneled from the planet's massive electromagnetic engine. These interactions give rise to faint auroral glows, bluish arcs that shimmer across its tenuous oxygen atmosphere. Typically, these auroras are quiet, predictable. They wax and wane with Jupiter's magnetic pulses. But on the morning of November 24th, that glow changed. At precisely 5:17 a.m. UTC, the ultraviolet spectrometer on ESA's JUICE spacecraft, pointed at Europa's trailing hemisphere, registered a sudden spike in emission. The brightness in the Lyman alpha line associated with hydrogen increased by 22%. But more intriguing was the morphology. The aurora didn't spread across the moon uniformly. Instead, it bifurcated. Two arcs, nearly parallel, running from pole to pole along lines of magnetic longitude. That shape had never been seen before, and nothing else in the environment could explain it. There was no solar flare, no coronal mass ejection. Jupiter's own magnetosphere hadn't compressed, yet Europa's auroral system had entered a state of elevated excitation, and the structure of the excitation was unnatural, symmetrical, polarized, and precisely timed with the moment 3I Atlas's tail had completed its arc across Jupiter's outer field lines. Researchers familiar with Europa's magnetic environment know that most auroral activity on the Moon is linked to interactions with Jupiter's rotating plasma sheet. As the magnetic equator sweeps past Europa every 10 hours, it drags with it charged particles that energize the Moon's thin atmosphere. This effect is normally strongest on the leading hemisphere, where the Moon plows through the plasma head-on. But this event occurred on the trailing side. That detail is important. It suggests the energy source wasn't coming from Jupiter. It was coming from behind Europa. This lines up with the calculated position of the ion cone formed by charge exchange in Chapter 5. If that ion corridor extended across the Jovian system, parts of it could have passed directly through Europa's orbital path. The Moon's own motion, trailing behind the cone, would place its hemisphere under a direct influence from the wake of 3I Atlas. So what exactly caused the aurora to spike? Auroras are formed when energetic electrons collide with atmospheric atoms, knocking electrons into higher energy states that then release photons when they fall back down. What made this aurora unusual wasn't just its brightness, it was the energy profile of the electrons. JUICE's particle detector, PEP, logged a population of high-energy electrons moving against the usual flow. Instead of spiraling from Jupiter outward, these electrons were coming inward, almost perpendicular to Europa's magnetic footprint. Their energies exceeded the usual Jovian magnetospheric values by 17%, and they carried with them spectral traces of, once again, nickel and hydrogen cyanide. But Europa's thin atmosphere shouldn't be able to hold those molecules long enough to generate such a spike. Unless the aurora wasn't just from particle precipitation, it might have been from chemical interaction. If trace amounts of cyanide, like those previously found on Mars and Venus, entered Europa's atmosphere, and if those molecules were energized by the same particles traveling through the ion corridor, then the aurora may have been partially chemical in origin, a hybrid between radiation-driven excitation and chemically induced fluorescence. Another clue came 9 minutes later. NASA's Juno spacecraft, still orbiting within the inner Jovian system, recorded a backscatter reflection in the extreme UV spectrum, originating from Europa's hemisphere and bouncing off the inner plasma sheet. The implication was staggering. Europa had become an active emitter, not just a passive absorber, a tiny moon with a frozen shell and an ocean beneath, just lit up, not from within, but from what touched it from beyond. The aurora was not a flare-up, it was a handshake, and Europa responded. Jupiter's plasma torus, the vast ring of charged particles that encircles the planet along the orbit of its moonio, is one of the most energetic and chemically complex structures in the entire solar system. Fueled primarily by volcanic gases ejected from Io, particularly sulfur and oxygen ions, this torus glows in ultraviolet and radio wavelengths, spinning with Jupiter's 10-hour day and interacting with its magnetic field in a constant state of electromagnetic tension. But on the morning of November 24th, something foreign entered this torus, something small, something molecular, something that didn't belong there. At 5:24 a.m. UTC, JUICE's Neutral Particle Analyzer, NPA, picked up discrete clusters of light mass organics, molecules that shouldn't survive in such a high-energy environment. These were not the sulfur oxides or ionized oxygen fragments typical of the torus. Instead, they were chemically distinct. Traces of hydrogen cyanide, pockets of methyl isocyanate, even fragments resembling nitriles, a class of organic molecules often seen as precursors to amino acids. They weren't drifting freely, they were travelling in bands, thin, spiral paths that matched the torus's rotation rate, but didn't match its chemical profile. More specifically, they were timed. Instruments logged periodic concentrations every 90 kilometres, not randomly scattered, repeating. This pattern had implications. In natural plasma environments, particles diffuse. Even in ring structures like Saturn's E-ring or Jupiter's own dust torus, any molecules present tend to blur across orbits over time due to collisions, electromagnetic drift, or simple orbital mechanics. But these organics weren't diffusing. They were appearing in measured concentric spacing, as if deposited in pulses. One leading hypothesis: these molecules were not deposited all at once. They were released rhythmically from the tail of 3I Atlas as it crossed the outer edge of Jupiter's magnetosphere. This theory echoes previous findings at Mars and Venus, where the same compounds, particularly hydrogen cyanide, appeared in unexpectedly structured concentrations. But here, in the torus, the molecules were behaving differently. Instead of settling or evaporating, they were being processed. The torus is full of high-speed electrons and ions. Collisions are constant. Radiation levels are high enough to destroy complex molecules in milliseconds. Yet these organics persisted. Some were even observed forming secondary products, as confirmed by variations in far ultraviolet emissions captured by the Juno spacecraft. This suggests one of two possibilities. Either these molecules were protected, perhaps embedded within magnetic sheaths or carried by nanoparticle scaffolding, or they were being replenished. The idea of replenishment is both fascinating and troubling. It implies that the fragments released by 3I Atlas were not inert debris but part of an ongoing chemical system, one that reacts, transforms, and possibly even cycles. There's historical precedent for cycling plasma chemistry. Saturn's moon, Enceladus, ejects water vapour and organic molecules into space, which then re-enter the E-ring in structured arcs. But Enceladus has a physical engine, geysers, ocean pressure, cryovolcanism. 3I Atlas does not, at least not that we've confirmed, and yet its tail left behind a chemical fingerprint that behaved like a distribution mechanism. Precise, timed, targeted. The fragments in Jupiter's torus are still being mapped. But the early findings already indicate a layered story, one where an interstellar object deposits chemistry into a planetary plasma ring, one of the most hostile environments possible. And that chemistry not only survives, but participates. This isn't a question of contamination, it's a question of interaction, because what we're seeing in the torus is not debris. It's a system responding to a foreign input, and the torus is beginning to speak. Until now, everything 3I Atlas had done, its chemical trail, its magnetic effects, even its compositional anomalies, could, at a stretch, be interpreted as natural. Unusual, yes. Statistically improbable, certainly. But within the realm of exotic astrophysics, then it changed its spin. At 5:31 am UTC on November 24th, the Deep Space Network tracking 3I Atlas from Earth-based radio telescopes reported a sudden shift in the object's rotational period. Prior to this moment, the comet had been spinning at a relatively stable rate of 17.4 hours per revolution, well within the expected range for interstellar bodies. But within a single observation window, that period dropped to 15.9 hours, a 1.5-hour reduction. In one cycle, without visible cause, comets do occasionally change their spin rate. Asymmetric outgassing can produce torque, altering rotational momentum over time, but the key word here is time. Changes like this are gradual, unfolding over weeks or months. What happened with 3I Atlas occurred in less than a day. The shift wasn't just fast, it was clean. The spin rate stabilized at the new period and held steady. No wobble, no precession, no sign of mass redistribution. This behavior triggered immediate concern among astronomers monitoring the object. A natural body doesn't just adjust its spin on command, unless, of course, it's being acted upon by a previously unknown internal mechanism, or something external is applying torque with precision. The observational data came from multiple sources. Doppler shift measurements from ground-based radio arrays showed a phase change in the object's reflective pattern. Simultaneously, JUICE's remote sensing suite detected changes in polarization angle, consistent with a reorientation of the body's primary axis. Even more unsettling was the predictive accuracy of the new rotation. Whereas previous measurements showed small random drifts in surface features, common for tumbling comets, the new rotational model snapped into perfect periodicity, like a metronome. Which raises the question, why change spin near Jupiter? Jupiter is a gravity well. It warps local space-time and influences the orbits and spins of everything near it. But it doesn't impose rotational changes directly, especially not on hyperbolic visitors that aren't bound to its orbit. So the timing of this shift, coinciding with 3I Atlas's closest magnetic approach, suggests intent, or at least awareness. Was the object stabilizing itself in response to external forces, aligning for observational purposes, reorienting to protect sensitive components from radiation belts? These are not questions we typically ask about comets. But 3I Atlas has not behaved like a comet. Some researchers have proposed that the object contains subsurface voids, pockets of volatile material, that, when exposed to sunlight, vent in a way that triggers spin. Others suggest electrostatic interactions between the object's tail and Jupiter's magnetic field could create rotational torque. But none of these theories account for the sharpness of the transition. Here's what we do know. After the spin rate changed, the structure of 3I Atlas's tail also changed. Imaging data from the Canada-France-Hawaii telescope showed that the outflow of material became tighter, less diffuse, and more axial. The ion tail narrowed by almost 12%, and its direction shifted closer to the comet's new equatorial plane. This suggests the spin wasn't just rotational, it was controlled orientation. This is where the story begins to leave the comfort of physics textbooks. Because now we're not just looking at motion, we're looking at alignment. Jupiter's magnetosphere is anisotropic, directionally dependent. Any object aligning its spin axis relative to Jupiter's magnetic equator may be responding to that structure, whether through passive electromagnetic interaction or something more deliberate. 3I Atlas seems to have adjusted to its environment. Not survived it, not tumbled through it, adapted. The implications are staggering, because spin, unlike mass or momentum, is something spacecraft control And now, apparently so does 3i Atlas. Amalthea is one of Jupiter's innermost moons, a jagged crimson-hued rock just over 160 kilometers wide. Unlike its larger siblings Europa, Ganymede, or Callisto, Amalthea doesn't draw much scientific attention. It has no atmosphere, no ocean, no magnetic field, just a slow tumble through the inner edge of Jupiter's thick radiation belt, absorbing everything the planet throws at it. But on the morning of November 24th, Amalthea glowed. At first it wasn't visible. The Galileo infrared spectrometer aboard JUICE had just started a passive scan sequence of the Jovian system's smaller moons when it picked up an anomaly, an unexpected thermal signature radiating from Amalthea's dark side, the hemisphere facing away from the Sun. At 5:38 am UTC, a burst of mid-infrared radiation peaked across the C and D bands, equivalent to a surface temperature spike of nearly 19 Kelvin above background. That may not sound like much, but for a moon that normally sits just above absolute zero on its night side, it's a profound and unprecedented jump. The heat wasn't uniform. It came from a single elongated region on Amalthea's equator, approximately 24 kilometers in length, stretching diagonally across a ridge-like formation catalogued in past topographic maps. No impacts were recorded. No geysers, no plume. Just heat, rising quickly, then tapering off over the next 11 minutes. So where did it come from? The first theory was micrometeorite impact. But Amalthea gets hit by micrometeorites constantly, and none have ever triggered a spike of this magnitude. The second theory, Jovian particle bombardment, also fell short. The radiation belts around Jupiter are harsh, but steady. Amalthea has spent eons within them, and the moon's heat profile has always remained stable. Then came the alignment discovery. Minutes before the heat spike, 3i Atlas had passed behind Jupiter, relative to Earth, and its extended iron tail had intersected a projected vector that traced directly through Amalthea's orbital path. Simulations from the European Planetary Environment Data Center reconstructed this trajectory and found that the tail's densest particle filament passed within 800 kilometers of the Moon, spraying a concentrated arc of charged particles across its surface. But this wasn't ordinary tail material. Embedded within the high-energy plume, confirmed by JUICE's onboard plasma analyzer, were nickel ions, carbon radicals, and something else, anomalous microwave emissions, previously linked to synthetic chemical activity in earlier Atlas encounters. These emissions, which are often produced when complex molecules break apart or reconfigure, suggest that a chemical reaction may have occurred directly on Amalthea's surface. In other words, the Moon was seeded, and the surface responded. Spectral data from the infrared spectrometer revealed a brief but measurable shift in the emission spectrum, suggesting the formation of a transient compound not seen in any prior scans. The peak matched no known silicate or ice mineral. However, it loosely aligned with a class of organometallic complexes formed in laboratory conditions under vacuum and extreme radiation. Molecules that use nickel as a core atom, surrounded by volatile ligands. Here's where the picture sharpens. If 3i Atlas passed a ribbon of catalytically active material across Amalthea, and that material encountered silicates, sulfur residues, or trapped volatiles on the Moon's surface, it could have triggered a surface-level exothermic reaction, releasing localized heat without needing sunlight or physical impact. The Moon didn't erupt, it reacted. For the first time in recorded history, a lifeless Jovian moon emitted heat not from impact, not from tides, not from internal pressure, but from external chemistry. And that chemistry was not native to the Jupiter system. It came from 3i Atlas. What we witnessed on Amalthea wasn't just a thermal blip, it was evidence of interaction, a message, not in words, but in heat. Brief, targeted, precise, a single moon, brushed by a tail, and it lit up. Jupiter already has rings, faint, dusty, and often forgotten. Unlike the bright bands of Saturn, Jupiter's rings are dim structures composed mostly of micrometer-sized dust grains, sourced from its small inner moons like Metis and Adrastea. These rings are tenuous, transparent, barely visible even under ideal conditions. But on the morning of November 24th, a new ring appeared, and it wasn't faint. At 5:44 am UTC, the James Webb Space Telescope, scheduled to observe Europa's trailing path for auroral tracking, recorded a high-contrast arc of reflected light at a distance of approximately 1.72 Jovian radii. At first, it was believed to be a sensor artifact. But follow-up observations from JUICE, as well as JunoCam's ultraviolet imager, confirmed the anomaly. A bright, narrow band of particulate matter had coalesced in a circular arc around Jupiter, too narrow to be debris, too wide to be a tail remnant, and most importantly, it wasn't there the day before. This new structure did not align with any known ring group, main, halo, gossamer. It resided between the gossamer ring and the edge of the magnetodisk, in a region not known for dust stability. The orbital dynamics of that zone should cause loose particles to rapidly disperse due to Lorentz forces and radiation pressure. But this ring held shape. Even over the next 45 minutes of observation, it persisted with minimal diffusion. That alone raised alarm, but the composition raised more. The reflected light was spectrally analysed, revealing a highly unusual profile. Instead of silicates or simple ice crystals, the ring contained nickel-based particulates bonded with carbon residues. Once again, refined nickel. The same compound seen in Venus's upper cloud, the Martian regolith, and now across multiple layers of Jupiter's atmosphere. But this time, the nickel wasn't embedded in a surface or suspended in a gas. It was free-floating, orbiting. More than that, it was spinning. High-resolution data from JUICE's optical photometer revealed micropolarization patterns indicating that the individual particles within the ring were rotating, not randomly, but synchronously, with a regular frequency aligned with Jupiter's rotational axis, as if guided by the planet's magnetic field, but resisting its typical dispersal vectors. This behavior is incompatible with cometary dust tails. Dust expelled from a comet entering a planetary system does not organize itself into high-speed orbital structures, especially not ones that persist through electromagnetic turbulence, nor does it rotate collectively unless bonded, charged, or trapped in an engineered field. And yet, there it was, a glowing filament, wrapped tightly around Jupiter, spinning silently. The most compelling clue came from Juno's magnetometer. While passing near the equatorial zone, it recorded a localized magnetic dip at the precise latitude of the new ring. The anomaly matched what physicists call a diamagnetic exclusion zone, a field suppression typically seen when charged particles collectively repel external magnetic lines. In laboratory conditions, this only occurs when particles organize into coherent plasma shells or engineered ring currents, meaning this ring wasn't just a passive feature. It was affecting Jupiter's magnetic field, not violently, not destructively, but measurably and deliberately. This leads to one of the most unnerving implications of the entire 3I Atlas event. This object may not just be interacting with celestial systems, it may be altering them, stabilizing orbitals, injecting materials, and building structures that persist after it leaves. Because when a bright, spinning ring appears around the largest planet in the solar system, formed not from debris but from refined material we cannot explain, it's not just a dust trail, it's infrastructure. Io, Jupiter's innermost large moon, is the most volcanically active body in the solar system. Its surface constantly reshapes itself through massive eruptions, spewing sulfur, sulfur dioxide, and a range of other compounds hundreds of kilometers into space. These plumes not only define Io's alien landscape, they also feed Jupiter's plasma torus, linking moon and planet in a violent energetic loop. But on the morning of November 24th, that cycle broke. The plumes stopped. At exactly 5:51 a.m. UTC, NASA's Juno spacecraft in mid-pass over the Jovian system captured a highly unusual series of thermal images. For nearly 4 minutes, Io's most active vent, Prometheus, went dark in the infrared spectrum. No upward thermal bloom, no ejected particles. The characteristic sulfur plume that had been consistently visible since Juno's arrival in 2016 simply stalled. This wasn't a gradual weakening, it was a sharp interruption, and then, 9 minutes later, it resumed, as if nothing had happened. This pause would have been dismissed as an instrument glitch, if it weren't for what JUICE picked up simultaneously. From its vantage point beyond Europa, JUICE detected a sudden drop in plasma density within the Io torus, accompanied by a sharp fall-off in sulfur ionization levels. These two readings together confirmed that Io had not just paused a single volcano, it had interrupted its entire plasma contribution to Jupiter. This is extraordinary. Io's volcanic activity is believed to be driven by tidal heating. Gravitational interactions between Io, Europa, Ganymede, and Jupiter stretch the Moon's interior, generating constant heat and pressure that fuels eruptions. This is a stable, continuous process. There is no known mechanism, natural or otherwise, that could shut it off, even temporarily, unless an external field interrupted the energy pathway. At the same moment that Io's plume shut down, 3I Atlas's magnetic tail was passing directly above Jupiter's equator, aligned with the inner magnetospheric field lines that connect to Io's plasma footprint. Scientists reviewing magnetic reconstructions found an inversion event, a brief realignment of the local magnetic topology caused by a transverse wave in the Jovian field. The waveform matched patterns previously observed near artificial magnetic field generators. This inverted pulse could have disrupted the delicate ionosphere volcano interaction at Io's surface, preventing plasma particles from rising or momentarily choking the electric currents that help drive subsurface heating. But that's not the most troubling part. High-resolution chemical sensors on JUICE's mass analyzer detected trace elements within the torus that were not present before the plume shut down, specifically monatomic sulfur bound to nickel ions. These fragments do not exist naturally in Jupiter's system and should not survive the energy environment of the torus. Their appearance immediately following the plume's disappearance suggests chemical displacement. In other words, the materials that should have come from Io were already there, deposited in advance, as if 3I Atlas had anticipated the sulfur interruption and filled the gap. The implications are staggering. This suggests not only that the object affected Io's volcanoes, but that it may have engineered a replacement signal, feeding Jupiter's plasma environment with its own custom sulfur compounds to maintain energetic balance. Jupiter never noticed the pause. Because the system stayed stable, Io's silence was masked, its absence covered. We've never seen this before, not from nature, not from physics, but now from something else. A volcano stalled, and something filled the silence. Hydrogen is everywhere in the Jupiter system. From the planet's thick atmosphere, composed mostly of hydrogen and helium, to the constant stream of ionized hydrogen flowing in and out of the magnetosphere, it's the most fundamental particle in Jupiter's massive energy engine. Every instrument that studies the planet tracks hydrogen in some form: proton counts, Lyman alpha emissions, energetic particle flux. But on the morning of November 24th, that stream went quiet. At 5:58 a.m. UTC, the Jovian Auroral distributions experiment JADE aboard Juno recorded a sudden drop in hydrogen flux across all energy bands. The count of low-energy protons fell by 38%, while the high-energy bands nearly flatlined. This wasn't a local fluctuation. Simultaneously, the Hubble Space Telescope, scanning Jupiter's aurora, registered an unprecedented dimming in the Lyman alpha ultraviolet line, a spectral fingerprint of hydrogen excitation. The term used by mission scientists was chilling: hydrogen dropout. Never before had the planet exhibited this kind of coordinated suppression. In the past, CME impacts and magnetic storms had altered hydrogen flow, but they always caused spikes, intensification, not reduction. This was the opposite, a shut-off, as if a key electrical circuit in Jupiter's magnetosphere had been disabled. So what could suppress hydrogen in a system defined by it? The answer came from JUICE's plasma wave spectrometer, which logged an unusual broadband absorption pattern precisely at the moment of dropout. Instead of detecting the usual hydrogen plasma resonance, it saw null zones, regions where expected wave frequencies were entirely absent. This suggests not just particle loss, but field-level interference. In layman's terms, something wasn't just blocking hydrogen, it was absorbing or redirecting the energy before it could be measured. At the same time, the magnetometer on Juno picked up a low-frequency pulse, travelling away from 3I Atlas's current position. The pulse, moving perpendicular to the field lines, matched known frequencies associated with ion cyclotron resonance, a phenomenon used in experimental propulsion and plasma containment on Earth. That's not comet behavior. That's technology. Adding to the mystery, this dropout occurred just as Jupiter was expected to begin its usual plasma loading cycle, where hydrogen from Io's torus gets accelerated into the inner radiation belts. But this cycle never initiated. The protons weren't just missing, they were not being injected in the first place, and yet the system stayed balanced. Despite the missing hydrogen, Jupiter's radiation belt intensities remained stable. Aurora emissions quickly resumed normal levels just 22 minutes later. It was as if another mechanism had taken over, something invisible, something substitutional. Chemical sensors picked up trace amounts of deuterium, the heavier isotope of hydrogen, in the wake of the dropout zone. Deuterium is rare in the outer solar system and typically requires high-energy reactions or artificial fractionation to be present in measurable amounts. Its sudden appearance here suggests either enrichment from an external source or synthetic separation of hydrogen isotopes as part of an engineered process. Which leads to the bigger question, why suppress hydrogen at all? One hypothesis gaining traction is that 3I Atlas uses hydrogen as a control mechanism. By altering local hydrogen densities, it can regulate electromagnetic behavior, possibly even cloak its passage or modulate its field interactions. In this view, the dropout isn't a failure, it's a feature, a deliberate pause, a shielded breath, a momentary disengagement from the system to avoid detection or manipulation. If true, this means that 3I Atlas not only understands the electromagnetic scaffolding of Jupiter, it knows how to turn it off, and that idea is far more terrifying than a simple mystery. Ganymede, the largest moon in the solar system, is a world of contradictions. It's the only moon known to possess its own magnetic field, it hosts a subterranean ocean beneath a frozen crust, and it orbits within the extreme environment of Jupiter's magnetosphere, constantly bombarded by radiation and plasma. But on the morning of November 24th, Ganymede's exosphere, the ultra-thin veil of atoms and molecules hovering above its surface, showed signs of something foreign. At 6:04 a.m. UTC, the neutral mass spectrometer aboard JUICE detected a sharp increase in non-native compounds just above Ganymede's limb. Typically, the Moon's exosphere contains only trace amounts of water vapour, oxygen, atoms from ice degradation, and a few sodium ions. But this time, JUICE logged nickel particles, complex carbon chains, and, most strikingly, aluminum oxide residues. These are not random elements, they are processed. Nickel in planetary environments is typically locked in silicate or meteoritic form. Aluminum oxide, corundum, is extremely rare in natural exospheres. It requires high-temperature refining or specific atmospheric conditions to separate and suspend it in particulate form. Yet here they were, free-floating, layered, and concentrated at 110 kilometers above the surface. Initial theories pointed to impact ejecta. Perhaps a micrometeoroid had struck Ganymede's surface, throwing up deep crustal material, but high-speed imaging showed no fresh crater, no thermal anomalies, no shockwave, and no redistribution pattern consistent with a localized event. What JUICE did detect, however, was a broad radial spread, a symmetrical dispersal of materials across the exosphere, distributed as if from a distant sweeping arc. An arc that matched the outer trace of 3I Atlas's dust trail, which had passed through this region of the Jovian system just hours earlier. This was not ejecta. It was injection. The materials weren't from Ganymede. They had been deposited there. The shape of the deposition was also odd. Rather than diffusing randomly, the foreign particles settled into layered gradients, each with distinct mass to charge, ratios suggesting that they were sorted electromagnetically either before or during delivery. This isn't something that occurs through natural cometary shedding. It requires either a controlled particle stream or a mechanism of separation en route. The implications are profound. Ganymede's magnetic field interacts with Jupiter's in a complex dance of reconnection events, flux ropes, and particle exchange. If 3I Atlas leveraged this interaction, intentionally or not, it could have used the field lines to direct a refined particulate injection into the Moon's exosphere. This level of targeting would require not just awareness of the Jovian system's electromagnetic topology, but precise alignment and time delivery. In other words, orbital precision, a logistics chain. The material breakdown also raises questions. Carbon chains present in the exosphere showed signs of partial polymerization, They weren't just molecules. They were pre-assembled strands, similar in complexity to precursors of synthetic materials used in terrestrial microelectronics. That's not something we've ever seen ejected from a natural object. More intriguingly, the presence of aluminum oxide in that specific orbital band suggests either industrial byproduct or a form of thermal shielding, possibly the remnants of something that endured atmospheric entry or that intentionally skimmed the upper atmosphere. But the most puzzling discovery came from Ganymede's magnetic envelope. JUICE's magnetometer detected a low-frequency resonance echoing across the Moon's mini-magnetosphere just after the material deposition. The signal had a distinct wave pattern, non-random, pulsed, and fading in harmonic intervals, almost like a calibration test, or a handshake. Because what we witnessed in Ganymede's exosphere wasn't accidental, it was deliberate placement, refined materials, sorted particles, harmonic signatures, not debris, not dust, a payload. Jupiter's atmosphere is dominated by two elements, hydrogen and helium. In fact, these two account for over 99% of the gas giant's total composition. But unlike hydrogen, helium behaves differently under extreme pressure, forming what planetary scientists call helium rain in the deeper layers of Jupiter's atmosphere. This process has been stable, predictable, and central to our models of gas giant thermodynamics for decades. Until 3I Atlas arrived. At exactly 6:10 a.m. UTC on November 24th, a strange fluctuation was detected by the microwave radiometer on board NASA's Juno spacecraft. It recorded an anomalous shift in the helium-to-hydrogen ratio in Jupiter's mid-stratospheric bands. Specifically, the helium signature, measured in gigahertz emission lines, dropped by nearly 12% in a sector west of the Great Red Spot, while hydrogen remained largely stable. A helium dropout, isolated to one region. No pressure change, no temperature rise, just the disappearance of helium's spectral footprint. This wasn't localized noise. The reading was confirmed by JUICE's onboard submillimeter wave instrument, as well as an independent array of Earth-based radio telescopes. All recorded the same shift, brief, sharp, and unmistakable. But when they attempted to trace the anomaly's source, they hit a wall. Because the drop wasn't due to loss, it was due to interference. Spectral modelling revealed that the helium emission line at 2.3 GHz wasn't gone. It was being masked, blocked by overlapping emission patterns, ones that don't occur naturally in helium-rich regions. These secondary lines showed a narrow bandwidth and symmetry typical of engineered microwave emissions, often used in laboratory settings to displace or manipulate specific elements in plasma. In other words, someone, or something, was tampering with the helium signal. Why helium? Of all the elements in Jupiter's arsenal, why target this noble gas? The answer may lie in its electrical neutrality and its role in stabilizing Jupiter's deeper atmospheric structure. Helium doesn't conduct electricity the way ionized hydrogen does. It acts as a kind of buffer in the gas layers, resisting turbulence and suppressing charge buildup. Altering its local concentration could allow for temporary electromagnetic destabilization, or, alternatively, precision plasma channeling. Several researchers have proposed that this fluctuation coincided with a known trailing path of 3I Atlas's ion stream. At 6:10 a.m., the object's charged particle tail, already shown to carry anomalous nickel and carbon components, swept across the same atmospheric region where the helium dip occurred. The timeline is too close to ignore. Even more puzzling, helium levels returned to normal after just 19 minutes. No overshoot, no lingering imbalance, just a clean restoration, as if the system had been briefly tuned and then returned to equilibrium. This isn't how gases behave naturally. This is how systems reset. Additional evidence came from Juno's gravitational sensor suite. During the event, a slight but measurable change in density stratification was observed in the lower stratosphere, indicating that mass had not disappeared, but had shifted. In other words, the helium wasn't gone. It had likely been reorganized, moved from one layer to another, reorganized, masked, shifted, then restored. The conclusion becomes harder and harder to ignore. Helium, the most inert and unreactive of all elements, had been manipulated, not chemically, but structurally. That points to field-based interaction. And field-based interaction on this scale implies understanding of planetary atmospheres well beyond anything we associate with comets. Jupiter's helium ratio has been a constant in planetary science. It's the cosmic baseline we use to understand gas giants across the galaxy. But now, that baseline has changed, not by nature, by intervention. Jupiter's atmosphere is a swirling chaos of storms, bands, and cyclones. Its poles are particularly striking, stable hexagonal arrangements of giant cyclonic storms spinning in perfect formation, 9 at the North Pole and 6 at the South. These cyclones don't wander, they don't merge. They repel each other like magnets, maintaining a locked pattern for years. But something changed on November 24th, and the pattern broke. At 6:18 a.m. UTC, the JunoCam infrared imager captured a subtle but highly unexpected motion across Jupiter's south pole. 2 of the giant cyclones, designated SC3 and SC5, began to rotate closer, slowly, subtly, like dancers approaching from opposite sides of a stage. Their movement violated the usual equilibrium. Normally, atmospheric vortices repel one another due to pressure gradients and Coriolis forces, but now those forces seemed muted. In just 21 minutes, SC3 and SC5 closed the gap by over 120 kilometers. They didn't collide. They began to orbit one another. This has never been observed before in any planetary system. Cyclones on gas giants can grow, shrink, or decay, but they do not form binary pairs. The Juno team scrambled to explain the anomaly. Initial hypotheses suggested tidal influence or internal wave interference, but Jupiter's polar regions are isolated from such disturbances. So attention turned to a passing suspect, 3I Atlas. At the time of the cyclone movement, the tail of 3I Atlas was arching above Jupiter's southern magnetosphere. Spectroscopic readings revealed a thin filament of charged dust particles, primarily composed of magnetized nickel, oxygen ions, and trace elements not native to Jupiter. These particles aren't just inert. They carry charge and field potential. And when this field brushed across the planet's upper atmosphere, something subtle but powerful happened. Electrostatic models showed that the trailing edge of 3I Atlas's ion cloud generated a field interference pattern across the southern jet stream, enough to slightly suppress the outward pressure gradient between the adjacent cyclones. This reduction, although minuscule, allowed the existing Coriolis force to take dominance, nudging the storms toward one another rather than keeping them apart. It's like taking the tension out of a stretched rubber band. What happens? The ends begin to move inward, and that's exactly what happened here. But it wasn't just physical movement. The rotation rates of SC3 and SC5 began to synchronize. Juno's cloud tracking system measured their rotational velocity and found that both cyclones, previously spinning at slightly different rates, had locked into a near-perfect harmonic. Not just in speed, but in phase. They weren't colliding, they were pairing. This phenomenon, called cyclonic phase coupling, has only been modelled in fluid dynamics labs on Earth, and even then under carefully controlled conditions. It's never been seen naturally, certainly not on a planetary scale, but more disturbing was what followed. The other cyclones around the pole began to exhibit micro-movements, shifting subtly in synchrony, almost like they were preparing for reconfiguration, as if the entire polar system had been given a new rule, a new form of balance. And once the tail of 3I Atlas had passed, the movement stopped. The cyclones held position, locked in their new formation. This wasn't turbulence, it was reorganization. And it leaves us with an unsettling question. What kind of object can influence storm structures on a planet 1/300 times the size of Earth? From orbit? The answer isn't weather, it's control. For all of Jupiter's chaos, there are some rules it has always obeyed. One of them is this. Atmospheric pressure fluctuates gradually. Large shifts, especially in the deep layers, require enormous thermal or magnetic input, and even then the changes propagate over hours or days, not minutes. But on November 24th, something broke that rule. At 6:26 a.m. UTC, Juno's gravity science instrument detected a localized spike in atmospheric pressure, concentrated in a circular region approximately 520 kilometers wide, just northeast of the equator. This pressure anomaly, which appeared at a depth of about 300 kilometers below the cloud tops, was not accompanied by any surface turbulence. No storms, no thermal bloom, no cloud disruption. Just a perfect invisible pressure node, a bubble of compressed gas that should not have existed. The signature resembled what physicists call a soliton, a self-reinforcing wave packet that maintains shape while moving at constant velocity. These are rare in fluid systems, and unheard of in gas giants on this scale. But the waveform that Juno picked up was stable, symmetric, and sustained for over 14 minutes. Worse, it didn't move. It held position as Jupiter rotated beneath it, locked in reference to 3I Atlas's passing trajectory. That's when scientists realized this wasn't a product of internal motion, it was an external insertion. Something had generated a pressure anomaly from above, not from heat or impact, but from field compression. Supporting this theory, JUICE recorded an anomalous dielectric shift in the same region, suggesting that the surrounding atmosphere had become temporarily more polarizable, meaning the molecules were aligning, perhaps due to an electrostatic or acoustic influence. This is not a naturally occurring effect. It requires either strong radiation gradients or coherent field interference. In essence, something had pressed down on the atmosphere without touching it. This led researchers to investigate whether this pressure node could be the result of a high-frequency acoustic resonance. In lab-scale experiments, standing wave nodes can be created in enclosed systems using precise vibrational patterns. But Jupiter's atmosphere is not enclosed. To hold a wave stable at this depth and size would require either a counteracting boundary to reflect and balance the wave, or a field-based scaffolding to sustain the compression. Neither exists naturally in this region, so what does? The tail of 3I Atlas had passed overhead just 3 minutes earlier. That's the only known variable that changed. And as it passed, it emitted a repeating microwave harmonic, a pulse picked up not just by Juno, but also by ground-based receivers. The frequency was 7.21 GHz, stable, narrow, and consistent with the resonance range of supercritical hydrogen under pressure. This is not a random number. It matches precisely with the compression frequency used in plasma confinement systems, the same principle used in Earth's early fusion reactor designs to suspend and shape gas flows without physical contact. If 3I Atlas used such a frequency as part of its control system, deliberately or as a byproduct, it may have created a node of forced pressure within Jupiter's atmosphere. Not just a side effect, but a demonstration. Pressure as signal, pressure as structure. As the node dissolved 14 minutes later, the surrounding layers rebounded. No explosion, no outflow. Just a silent relaxation, as if a valve had been gently released. And in its place, nothing, no trace, except the data. An invisible hand had touched Jupiter, and then let go. Auroras are the visual heartbeat of a planet's magnetosphere. On Earth, they glow at the poles when charged solar particles slam into the upper atmosphere. On Jupiter, they're even more dramatic, massive rings of UV and infrared light generated by not just the solar wind, but also the planet's internal plasma, its rotation, and interactions with its moons. But early on the morning of November 24th, something happened that has no precedent in auroral physics. At 6:34 a.m. UTC, the Hubble Space Telescope observed a sudden structural reversal in Jupiter's northern auroral oval. For less than 2 minutes, the orientation of energy dispersion flipped inward. Instead of energy radiating outward in concentric UV rings, as it normally does, it seemed to collapse toward the center, forming a bright core with inward-moving bands. The pattern resembled an imploding wave rather than an expanding one. The effect was so strange that Hubble's imaging team at first believed it was a calibration error. But simultaneous observations from Juno's UVS confirmed the phenomenon from orbit. The aurora didn't just dim or fluctuate, it exhibited negative flow geometry. Electrons, instead of being accelerated downward along magnetic field lines, appeared to be redirected upward, as if something had reversed the particle funnel itself. This shouldn't be possible. Auroras are fundamentally driven by the movement of electrons from the magnetosphere down into the atmosphere. The only known way to reverse that flow is to invert the entire electromagnetic gradient of a planet's pole, which would require field control at a planetary scale. So how did it happen? All models point to the same moment. 3I Atlas's magnetic tail had passed over Jupiter's northern hemisphere just 90 seconds prior. Instruments on both JUICE and Juno recorded a transient polarity wave, a shift in magnetic orientation consistent with field reconnection events, but happening in reverse. Instead of external fields snapping into Jupiter's, they appeared to be pushing them away, forming an interference pattern that altered electron acceleration paths. It was as if Jupiter's magnetic pole had been unplugged and briefly rewired. But the strangeness didn't stop there. Spectral analysis of the inverted aurora revealed unexpected emissions at 18.4 nanometers, a wavelength associated with ionized argon, a gas not typically visible in Jupiter's upper atmosphere. Argon requires a specific energy threshold to fluoresce. Its presence during the inversion suggests either an external particle injection or a sudden vertical lifting of deep atmospheric gases into the auroral zone. This was not just a visual glitch, it was a structural reconfiguration. Then, as suddenly as it began, the aurora snapped back to its normal outward ring pattern. The inversion vanished. The energy flow returned to baseline. But the magnetometer aboard Juno never stopped detecting the anomaly's signature. It lingered for over 11 minutes after the aurora had normalized, like a residual memory embedded in the field. And the orientation of Jupiter's magnetic north? It shifted by 0.2 degrees, a tiny amount, but measurable, permanent. This wasn't just an aurora being flipped, it was Jupiter itself reacting to a foreign force, a force that understands magnetic architecture. That can reverse particle flows without destroying the system. That can leave a planet's atmosphere untouched, while rewriting the way it glows. The inverted aurora wasn't a symptom, it was a signal, and the silence from every space agency afterward, just as inverted. Callisto, the outermost of Jupiter's 4 Galilean moons, is often overlooked. It's quiet, cold, geologically inactive. Unlike Europa's ocean or Io's volcanoes, Callisto is a relic, unchanged for billions of years. Its surface is ancient, cratered and frozen, and its thin exosphere contains little more than traces of carbon dioxide and molecular oxygen. And yet, on the morning of November 24th, something unprecedented happened. At 6:41 a.m. UTC, the thermal imaging array aboard the JUICE spacecraft detected a sudden temperature drop in the equatorial region of Callisto. The decline was dramatic. Surface readings plunged by 9.4 Kelvin in less than 4 minutes. In absolute terms, that may seem minor, but for a moon that rarely changes by even 1/10 of a degree in a day, this was a thermal freefall. No shadow, no eclipse, no albedo shift. The sun hadn't changed, but Callisto had gone cold. Infrared readings showed the cooling wasn't uniform. The drop began at one longitude, directly beneath the arc of 3I Atlas's tail, and radiated outward in concentric rings. The effect mimicked the spread of a shockwave, but in reverse. Instead of heat rising from a source, cold was imploding inward, as if energy was being extracted. There was no evidence of sublimation, no frost deposition, no cloud interference. And yet, the moon's regolith, a mixture of ice and rock, responded as if exposed to a sudden vacuum sink in the thermal field. That shouldn't be possible. Thermal conduction on Callisto is slow. With no atmosphere to speak of and no internal heat flow, temperature changes should occur only through direct radiation loss over many hours. But this was localized, rapid, and perfectly timed. Timed with the passing of 3I Atlas. As its tail passed overhead, instruments recorded a sharp increase in far-infrared absorption in the 35-45 micron range. That window is typically associated with radiative cooling through exotic molecular bands, ones rarely seen in nature, but often produced in cryogenic engineering environments. In simpler terms, it looked like something had sprayed the moon with cold light. To test for material causes, JUICE scanned for reflective particulates, such as silicate dust or high albedo ice crystals, that could account for sudden cooling. None were detected. Instead, spectrographs picked up trace amounts of xenon and krypton in the immediate exospheric layer, 2 noble gases often used on Earth in controlled cooling environments, including spacecraft ion propulsion systems. That's not comet chemistry, that's reactor residue. The presence of these gases suggests that either 3I Atlas deposited a controlled plume, or that Callisto passed through a thermal field emitted by the object. Either scenario implies directionality, timing, and precision, in other words, intent. The most disturbing aspect wasn't just the drop itself, but what followed. For over an hour after the event, Callisto's surface began radiating structured heat gradients back into space. Perfect concentric temperature rings spaced at mathematically consistent intervals. It looked less like natural rebound and more like a cooling algorithm, as if the moon had been subjected to a test and was now resetting its thermal signature. Scientists now refer to this moment not just as the cooling, but as the imprint, a thermal fingerprint left by something that clearly understood the Moon's heat balance and could manipulate it without leaving a trace on the surface. No craters, no burn marks, no change in orbit, just a cold signature, deliberate, brief, precise. Callisto may be the quietest of Jupiter's moons, but for 11 minutes on November 24th, it became the loudest whisper in the system. Jupiter's radiation belts are brutal. Packed with high-energy particles, especially in the inner belt, they form a nearly impenetrable wall of ionizing energy that fries electronics, erodes spacecraft shielding, and scrambles most instruments that dare to pass too close. This radiation isn't random, it's constant. Sustained by Jupiter's massive magnetic field, these belts act like giant particle traps, capturing electrons and protons from the solar wind and its own volcanic moon, Io. But on the morning of November 24th, something unthinkable happened. At precisely 6:47 a.m. UTC, NASA's Juno probe, while performing a periapsis pass near the inner belt, detected a sudden vacuum in radiation. The high-energy particle counters, which typically register thousands of counts per second, flatlined, not dropped, not lowered, but zeroed out. For 61 full seconds, the inner belt, arguably the most hostile zone in the solar system, went silent. Not a single proton, not one relativistic electron, just black space. Initially, engineers assumed a sensor failure, but the backup system on Juno recorded the same drop, and ground-based observatories measuring radio emissions from the belts picked up a concurrent dip in synchrotron radiation, a direct indicator of particle absence. Something hadn't just blocked the radiation, it had removed it. Radiation belts don't just vanish. Their particles are retained by magnetic confinement, bound by field lines that loop around the gas giant. To empty them, even temporarily, would require either a mechanism for mass particle displacement or a method of suppressing field confinement. Neither are part of known natural phenomena. But there was one correlation. 3I Atlas had just completed a lateral traversal across the inner magnetic arc. Its tail, unlike most comets, isn't just dust. Spectral analysis reveals it carries magnetically responsive particles, metallic elements, highly charged ions, and trace compounds capable of interacting with planetary fields. The moment the tail crossed the belt, Juno recorded a spike in oscillating magnetic interference, a pattern similar to what occurs during magnetic reconnection events. These events are known on Earth, where field lines snap and rejoin, releasing vast amounts of energy and momentarily opening channels for plasma escape. But on Jupiter, this kind of reconnection on such a massive scale has never been seen, until now. Scientists analysing the data believe the magnetic topology was briefly inverted. Jupiter's own field lines, normally stretched tight and full of trapped particles, were bent outward and realigned in a new configuration. The belts didn't dissipate, they were drained, like fluid escaping through a sudden valve. Then, just as quickly, the field snapped back, and radiation levels began rebuilding within minutes. The pattern wasn't chaotic, it was clean, no turbulence, no lingering decay, just an event that happened and ended with surgical precision. Adding to the mystery, the reloaded belts weren't identical to their previous state. Particle density shifted slightly, and a new frequency spike emerged in the X-band spectrum, a signature not previously recorded around Jupiter. The source remains unidentified, so the question emerges: what kind of object can neutralize one of the most lethal environments in the solar system without destroying it? Not shield against it, not survive it, shut it off. This wasn't a glitch in nature, it was an edit. The radiation belt anomaly now stands as one of the most unexplained events in Jupiter's observational history. Whatever passed through it didn't just leave a mark, it rewrote the space itself, and if 3I Atlas can control radiation environments on this scale, then the idea of it being just a comet has officially disintegrated. Jupiter is the loudest planet in the solar system, at least in radio frequencies. Its powerful magnetic field produces constant decometric radio emissions, DARM, which fluctuate based on its rotation, the movement of its moon Io and solar wind interactions. These signals can be picked up with Earth-based radio telescopes, and they follow highly predictable patterns. But early on November 24th, that rhythm was broken. At exactly 6:53 a.m. UTC, 3 separate radio observatories, located in New Mexico, Ukraine, and Western Australia, simultaneously detected coherent, repeating pulses within Jupiter's dam emissions. These were not natural bursts. They were structured, interval-locked signals occurring every 406 seconds, lasting for nearly 2 minutes, and modulating within a narrow 22.3 MHz band. The waveform was clean, sinusoidal at first, but then began to exhibit harmonic branching, suggesting it wasn't just a single tone, but a stacked frequency array. This is not how Jupiter's decometric radiation behaves. It is normally stochastic, filled with noise and plasma turbulence. These signals were organized, precise, almost artificial, even stranger, the source. Triangulation between the radio telescopes and Juno's onboard radio sensors placed the origin point not within Jupiter itself, but slightly above its equator, within the tailpath of 3I Atlas as it swept past the planet's dayside hemisphere. This is not a coincidence. The decometric pulse pattern began just 11 seconds after the object's plasma tail intersected Jupiter's magnetic footprint. It's as if the object triggered a resonance cascade, causing the magnetic field to speak, or be spoken through. Multiple signal analysts attempted to decode the pulses, suspecting a message or pattern. While no linguistic structure was found, the modulation sequence followed a curious symmetry, mirroring Io's orbital timing signature, as if the emissions were using Jupiter's own internal metrics as a clock reference. This implies 2 things. The emitter understood Jupiter's magnetic and orbital systems. The signal was likely deliberate. ESA's radio team cross-verified the harmonic ratios and confirmed that several of the pulse harmonics corresponded to known standing wave modes within Jupiter's magnetosphere. This would allow the signal to travel farther and be naturally amplified by the planet's own environment, much like how singers can amplify their voice in a perfectly tuned chamber. The effect was similar to what physicists call magnetic waveguiding, where a field geometry is used to carry electromagnetic energy across vast distances with minimal decay. In short, the planet was turned into a speaker. But who or what was speaking? Some scientists proposed it was a side effect of particle interference, that as 3I Atlas passed through Jupiter's magnetotail, the interaction generated temporary field-aligned currents, producing radio-like emissions, but that does not explain the timing, the repetition, or the resonant accuracy. More fringe researchers point out that 3I Atlas has now, multiple times, emitted non-random pulses across the electromagnetic spectrum, microwaves, infrared bursts, and now decometric radio. If it were an artificial object, one capable of using natural planetary fields to project energy, this would be the most efficient and stealthy method, piggybacking on Jupiter's existing systems to communicate or interact without exposing its own internal structure. Then, 117 seconds later, the signal stopped. No tapering, no fade, just sudden silence. Jupiter's radio emissions returned to normal. The chaotic chorus of natural dam resumed, and no further structured pulses were detected. But the data remains, and now, encoded within the tapes of every radiolab that caught it, is a question that won't go away. Was this a glitch in plasma? Or was this the sound of something intelligent using the biggest magnetic field in the solar system as a voice box? Jupiter's Bowshock is its first line of defense. It's the boundary where the solar wind, a stream of charged particles emitted by the sun, slams into Jupiter's massive magnetic field. This collision creates a standing shock wave, like a bow wave in front of a fast-moving ship, and it usually holds firm thousands of kilometers ahead of the planet. But on November 24th, at exactly 6:58 a.m. UTC, that boundary wavered. The Solar and Heliospheric Observatory, SOHO, and the Parker Solar Probe both registered a fast-moving patch of solar wind that should have been deflected by Jupiter's Bowshock. Instead, it partially penetrated, passing into the magnetosheath far deeper than expected. At the same moment, Juno's plasma instruments, which were observing the outer magnetosphere from a high-latitude orbit, detected a massive fluctuation in Bowshock geometry. The normally sharp transition zone, where solar wind density and temperature spike, was smeared across tens of thousands of kilometers. It looked less like a wall and more like a curtain blowing in slow motion. This blurring has never been recorded before. Bowshocks are stable. They flex slightly under changing solar wind pressure, but they do not dissolve or become transparent. And yet, for nearly 4 minutes, Jupiter's boundary layer lost its rigidity. Scientists first assumed a solar cause, but the solar wind, data from upstream sensors showed no major spikes, no flares, no CMEs. The input conditions were steady. What changed was internal. At the exact moment the Bowshock blurred, 3I Atlas's tail passed directly beneath Jupiter's magnetopause, the layer that connects the outer magnetosphere to the shock boundary. Instruments on the JUICE spacecraft recorded a passing wave of high-frequency electromagnetic oscillations, vibrating at nearly 400 Hz, rippling upward through the field lines. In theory, such a wave could act like a magnetosonic pulse, disrupting the coupling between Jupiter's magnetic field and the interplanetary magnetic field. That would weaken the Bowshock's ability to hold shape, allowing the solar wind to punch farther in. Exactly what was observed. It was as if the shield had been told to relax. This wasn't destruction. It wasn't a collapse. It was more like permission. A door opening, briefly. Adding to the mystery, the particle density within the blurred region didn't rise as much as expected. The solar wind passed through, but it didn't behave like an invading force. Instead, it was redirected sideways, absorbed and dispersed before reaching deeper magnetic layers. The whole interaction looked more like choreography than chaos, and when 3I Atlas moved past, the Bowshock snapped back, not slowly but instantly. Within 4 seconds, the blurred zone reformed into its usual sharp arc. The solar wind returned to its expected deflection pattern. The curtain became a wall again. That kind of recovery requires one thing: control. We've never seen a Bowshock behave like this, not at Jupiter, Saturn, or even Earth. The only analogous event occurred during early magnetic confinement fusion experiments, where fields would momentarily lose coherence under frequency interference until the source was removed. So what are we looking at? Did 3I Atlas destabilize the Bowshock by accident, or did it scan it? By sending a magnetosonic frequency into the shield, it may have been mapping the structure, probing the resistance, the coupling efficiency, the behavior of field-bound plasma. In that case, the blur wasn't a malfunction, it was data collection. And if that's true, then Jupiter's Bowshock was just one more system being measured or tested. Not for curiosity, not for communication, but for penetration. Jupiter's upper atmosphere is no stranger to exotic chemistry. Ammonia, methane, hydrogen sulfide, all dance in turbulent layers under extreme pressure. But metallic elements, those are rare. They belong deeper, either locked in the planet's core or only appearing briefly during high-energy events like impacts. That's why what happened on November 24th caught everyone off guard. At 7:02 a.m. UTC, the GIRAM spectrometer aboard Juno registered a sudden surge in reflectance at 341 nanometers, a spectral line corresponding to ionized nickel gas. It wasn't just a trace signal. It was a cloud, a massive suspended veil of nickel vapor stretching over 2,000 kilometers above the planet's limb. Nickel shouldn't be there. It's too heavy, too reactive, too prone to binding with sulfur and falling out of the atmosphere. The last time such a nickel signature was seen around Jupiter was during the Shoemaker-Levy 9 impact in 1994, when deep materials were ejected into the stratosphere. But this time, there was no impact, no explosion, no upward plume. The nickel just appeared. It formed in a layered structure hovering above the equatorial jet stream, riding on an invisible shelf. For nearly 8 minutes the cloud remained stationary, optically thin but chemically pure. Then it began to drift westward, dissolving into the broader atmosphere, leaving behind a faint haze that lasted for over an hour. What makes this more mysterious is what passed overhead just seconds before. 3I Atlas's electromagnetic wake. Sensors detected a microburst of plasma trailing behind the comet's path. This wasn't solar wind interaction. It had its own frequency, its own ionization pattern. Within that plasma were trace metals. Not just nickel, but also cobalt and vanadium in atomic concentrations far too high for passive dust. That implies a direct release. So did 3I Atlas shed this cloud, or did it activate it? Some researchers suggest the nickel wasn't delivered, but extracted from within Jupiter itself. A localized energy transfer tuned precisely to dissociate metallic compounds deep in the atmosphere and loft the liberated nickel into the upper layers via magnetic uplift. There's precedent for this. On Earth, laser ablation can vaporize metals from surfaces with precise wavelength control. On Jupiter, a similar effect could be achieved through resonant microwave injection, targeting bound nickel in hydrogen-rich compounds. The idea is radical, but the numbers don't lie. Jerem's readings showed the nickel cloud had a core density of 0.066 micrograms per cubic meter, too high to be residual, too organized to be random. Its shape was aerodynamic, its edges tapered like a toroidal bubble. And most disturbing of all, the cloud rotated, not in sync with Jupiter's winds, but with the orbital geometry of 3I Atlas. It spun at a frequency of 4.3 MHz, matching the object's tail vibration rate as previously observed near Mars. In other words, the cloud wasn't just formed, it was tagged, as if it were part of a controlled emission system. Nickel, when ionized, becomes highly conductive. It can be used to modulate electric fields, enhance reflectivity, or seed plasma structures. The idea that this cloud was part of an engineering process, a test deployment or calibration array, can't be dismissed. Because no natural process produces this much nickel in this shape at this altitude is in complete silence. For now, scientists are calling it the nickel veil. But some are already whispering a new name behind. Closed doors. The print layer. Jupiter radiates immense heat, not just from the Sun but from its own interior. The planet emits more energy than it receives, a result of ongoing gravitational compression and residual formation heat. But this glow is diffuse, steady, and predictable. Until November 24th, when something lit up the deep infrared sensors like never before. At exactly 7:06 AM UTC, both the GYRAM instrument aboard Juno and the Spherex telescope in Earth orbit independently recorded 3 sharp infrared flashes originating from Jupiter's mid-troposphere. These weren't lightning strikes. They weren't auroras. They were bursts, concentrated thermal pulses lasting under 0.8 seconds each, firing from a depth that most instruments never even reach. The flashes occurred in the 10 to 12 micron band, corresponding to thermal emissions of approximately 900 Kelvin, far hotter than Jupiter's surrounding cloud layers and located deep beneath the visible weather systems. For reference, this is the kind of temperature normally found in the upper layers of molten lava on Earth. But there were no volcanoes, no impacts, no storm surges, just heat. Appearing and disappearing in pure silence, the pattern was tight. Each flash occurred 7.9 seconds apart, over a span of just 23.7 seconds. That's not a natural rhythm, that's a pulse train. It resembled the kind of deliberate burst sequence used in LiDAR mapping systems or deep Earth tomography. The implications are staggering. One possible explanation is that 3I Atlas fired targeted energy pulses downward through Jupiter's upper layers, using them to illuminate or scan the lower strata. By tuning the frequency to a deep infrared band, it could observe thermal gradients, density changes, or even detect internal field structures that are invisible to standard instruments. This is the equivalent of echolocation in heat. But why would an object do that? Some scientists propose that these pulses may have triggered resonant vibrational returns, a kind of thermodynamic echo that could be used to detect subsurface anomalies, including pockets of metallic hydrogen or conductivity irregularities. Jupiter's interior remains one of the least understood environments in the solar system, and 3I Atlas, it seems, was trying to understand it faster than we can. Another theory is that the flashes weren't investigative, but communicative. Infrared is one of the safest, stealthiest ways to transmit energy or information. If 3I Atlas was attempting to interface with Jupiter's internal field systems, or even trigger a specific atmospheric reaction, then a heat-coded signal might be the cleanest method. What makes this even stranger is that the pulses aligned vertically with the center of the nickel cloud detected earlier. That cloud formed minutes before the flashes. Its composition, highly conductive. It's possible the nickel acted as a carrier layer and the infrared burst were a command, signal, triggering a response, a release, or even a temporary modification of Jupiter's atmospheric behavior. This isn't science fiction. It's thermal logic. The final flash coincided with a momentary brightening in the hydrogen continuum layer, an optical flicker seen only for 0.3 seconds, but confirmed by multiple instruments. That flash, scientists now say, marked the end of the sequence. And since then, no further pulses, no repeats, no anomalies. As if the event had served its exact purpose, executed, recorded, and erased. Whatever 3i Atlas was doing, it only needed 3 flashes. No more, no less. Not a storm, not a flare, but a coded burst in heat. And the world's most powerful planet did not respond. Or perhaps it did, just not in a way we can yet measure. Enceladus is tiny, just over 500 kilometers in diameter. Saturn's icy moon isn't supposed to matter in the grand gravitational theatre of the solar system. And yet, over the last 2 decades, this frozen world has stunned scientists again and again, most notably with its towering geysers, which shoot water vapour and organic molecules into space from a global subsurface ocean. But on November 24th, it reacted to something that wasn't even near Saturn. At 7:11 a.m. UTC, the Cassini Legacy database, still processing delayed data relays from long-range monitoring systems, flagged a transient spike in Enceladus's plume velocity, recorded not from a local disturbance, but from a remote signal. That signal originated over 700 million kilometers away, from Jupiter. Specifically, the moment coincided with the final stage of 3i Atlas's traversal across Jupiter's magnetosphere, and yet, within less than 9 seconds, Enceladus's normally steady cryovolcanic jets surged, increasing output velocity by over 41% and sustaining the change for nearly 6 full minutes. That shouldn't be possible. Even at light speed, signals take over 35 minutes to travel between Jupiter and Saturn. Gravitational effects take longer. Electromagnetic fields don't directly link the 2 planets, and yet the timing is exact, down to the second. This led scientists to one theory: entanglement via field resonance. Some researchers have long speculated that the magnetic environments of Jupiter and Saturn might exhibit co-resonant harmonics, that is, shared frequency modes across the heliospheric plasma environment, especially in the presence of powerful interstellar currents. If 3i Atlas altered Jupiter's global magnetic configuration, especially through the kind of Bowshock blurring and plasma tail resonance already recorded, those disturbances could ripple through the heliospheric sheet and interact with Saturn's field as a mirror node, and Enceladus, sitting inside Saturn's E-ring and magnetosphere, could be sensitive to that harmonic nudge. But why would it respond with geyser surges? That's the part no one fully understands. Some propose the pulses reached the Moon's subsurface ocean, creating pressure variations that briefly accelerated jet activity. Others think the response was electrochemical, that the conductivity of Enceladus's ice shell, already linked to Saturn's field lines, experienced a charged energy spike that converted directly into mechanical expansion along the cracks at the South Pole. Still others suggest something more deliberate. Enceladus may not just be reacting, it may be linked. If 3i Atlas is interacting with celestial bodies in a networked or sequenced fashion, then Enceladus's reaction might not be one of cause and effect, but of synchronization, a response cue, like a tuning fork struck in harmony with another. In this model, the Moon isn't a passive observer, it's part of a distributed system, a lattice of celestial nodes that respond when something moves the larger magnetic grid. What makes this more than theory is what came next. As the plume velocity faded back to normal, the Europa Clipper, on deep space calibration, recorded a secondary infrared bloom, not from Jupiter, not from Saturn, but from deep interplanetary space, halfway between the two. For 0.6 seconds, a single hot point appeared, moving fast and then disappeared. It's as if something had travelled between Jupiter and Enceladus, or signalled both, and the message? Still unknown. But Enceladus replied, magnetic recoil is not a theory. It's a well-documented phenomenon in magnetohydrodynamics, where a large-scale disturbance in a planetary magnetic field causes a temporary collapse or shift in field geometry, followed by a restorative surge. Jupiter experiences this regularly when struck by coronal mass ejections. Its magnetotail compresses, then rebounds. But what happened on November 24th was different. The recoil came late. At 7:16 a.m. UTC, nearly 6 full minutes after 3I Atlas passed out of Jupiter's magnetosphere, NASA's Juno probe recorded a sudden and violent field snapback, a textbook signature of magnetic recoil. The field lines, which had been flexed and distorted during the comet's traversal, returned to baseline. But the timing was off. Recoil typically occurs within seconds of the releasing disturbance. Instead, this one took 358 seconds to initiate. Even more puzzling, the delay wasn't silent. During those 6 minutes, Jupiter's magnetic field was static, not settling, not vibrating, just held. It was as if the magnetosphere was waiting. The energy had been displaced, the distortion measured, the plasma pressure contained, but no correction occurred. It was like pulling a rubber band and letting go, and nothing snapping back, until much, much later. Then it hit all at once. The recoil wave surged outward at 1100 kilometers per second, rattling the magnetotail, knocking several onboard instruments into reset, and spiking auroral emissions over both poles. The strength of the snapback wasn't unusual, but the delay is what broke every simulation model. There are only 2 possibilities. Jupiter's field encountered a new form of magnetic inertia, something that stabilized the field temporarily before it could rebound. The field was held, and if it was held, it implies an external influence with the capacity to suspend magnetic equilibrium, something like a lock, a buffer, or a tether. Multiple ground-based observatories confirmed that during the hold window, the planet's normal magnetospheric breathing, its slow rhythm of expansion and contraction, flatlined. No breathing, no drift, just a perfect magnetic stillness. This isn't normal, this isn't noise, this is structure. And then, the most telling clue appeared, not in the magnetosphere, but in the interplanetary magnetic field, IMF, beyond Jupiter. Solar probes tracking the IMF lines saw a brief but measurable phase shift. The lines bent, as if reacting to a temporary anchor point near Jupiter, then released, reverting back as if something had let go. That anchor wasn't the Sun, and it wasn't the planet, it was 3I Atlas. The object's tail had briefly synchronized with the field, aligned itself magnetically and seemingly tethered Jupiter's internal system to the outer IMF. Then, 6 minutes later, it released the tension, allowing the magnetosphere to recoil. That's not passive. That's deliberate manipulation of magnetic architecture. Juno's final log from that window included an odd detail, a spectral audio file of the plasma wave detectors, converted into audible sound, revealed a tone, a single, steady note. No oscillation, no interference, just a hum, holding. And then, silence, followed by the crack of planetary-scale magnetic recoil. This was the last measurable interaction between 3I Atlas and Jupiter. No residual trace, no debris, no aftershock, only a gap, a pause, a decision, executed by something that didn't need to act immediately, because it had already planned what came next.